Welcome back. So, yesterday we were discussing about similarity matrix, and let me begin with the advantage of this similarity matrix. So, this is our so A is introduced notation yesterday. So, this is an n by n real matrix. Okay. We call A is similar to B. So, suppose there exists non-singular C belonging to M and R such that C inverse A C equal to B. Okay. So, this is we say that A and B are similar. So, we are aiming at finding a suitable C such that this B is either diagonal or, in the worst scenario, an upper triangular matrix. We will come to this little later. And we also saw that, so this implies C inverse E A, C is equal to E to the B. Okay, so, the exponentials of A and B are also similar. In the context of ODE, so let us consider this x dot equal to A x. Suppose this is the given system, and we know that the general solution is given by e to the T A and x naught. X naught is an arbitrary vector in R n, and now through similarity transformation we transfer this given system into y dot equal to B y, and similarly y is t is given by e to the T B some y naught. Okay. And when B is this simple either diagonal or upper triangular, this is very easily computed. Not only that, we can easily analyze the qualitative behavior of this y t, and how x and y are connected is very easy. So, you put y is equal to C inverse x, and so this y naught will be just C inverse x naught, and once we know y, so it is easily we can also analyze x since x is C y. Okay. So, that is the advantage. Okay. So, that is why this all effort is being done to find a suitable non-singular C such that the C inverse is equal to B, and B is quite simple one. So, that we can compute the exponential of T B very easily, and then we analyze the solutions of this reduced system, and then we get information about the original system. Okay, that is the advantage. Okay. So, let us now begin with this thing. So, before going to that thing, so just let me again make a few remarks. So, so by the definition of the norm, it follows that norm of A x is less than or equal to norm A norm x for all x in R n. Okay. We also saw that we saw this A is less than or equal to this Frobenius norm. Okay, so this is Frobenius norm. And from this, if I replace x by x minus y and by linearity of A, so we have Ax minus Ay less than or equal to norm A x minus y, and that proves this function x going to Ax is Lipschitz continuous. More is true. So, suppose At is a matrix valued function of t in some interval. So, that means for each t in AB, At is in MNR, okay? And suppose and assume the elements of At are continuous on AB, okay? And then then this for each t I have this thing, and since this Frobenius norm is sum of all squares of the elements of At, and since I am assuming they are all continuous, so this is just a sum, let me put m for all t in AB using continuity of the elements of At. Okay. So, this implies, so we have this useful inequality is less than or equal to m x minus y for all t in AB. So, that means this matrix, the x going to ATX is uniformly Lipschitz in this interval, and this is, we use this fact in studying the linear system x dot equal to ATX. And because of this global existence, the solutions exist in any interval where At is continuous. Okay. So, with this little remark, so let us again go back to linear algebra, more linear algebra. As I said yesterday, this is not a course on linear algebra. So, I am just recalling certain facts that are used in our study of differential equations. So, suppose M and N are subspaces of Rn such that, so since they are subspaces, 0 element is always there, and I just want their intersection to be just 0. We call such subspaces, we call Mn disjoint. Okay. So, though the intersection is not empty, but it is the trivial subspace, namely the 0 subspace, we still call it disjoint. and assume R n is m plus n. Okay. Let me explain that little bit. So, this is called direct sum of m n. Okay. This means each vector in R n is written as a sum of a vector in M and a vector in N. Okay. And this condition M n are disjoint. Okay. So, you can easily check that R n is equal to m plus n direct sum m if and only if for all x in R n there exists unique y in m and z in n such that x equal to y plus z. Okay, that should happen. And this is easily extendable to any finite number of subspaces, and that is what we are going to do. Okay. So, in addition, suppose m n are invariant under A. So, remember A is given matrix n by n matrix. So, that is again definition A m. So, you act A on every element of m and again that should be in n, and similarly for n. Okay. So, this means you act A on every element of m and again the result should be again back in m. Okay. In this situation, suppose we choose a basis in m and a basis in n, and if you put together that will be a. So, I will just write okay, this and this will form a basis in R n. Okay. Now, you take those basis elements and form this matrix C. Okay. So, this is C and these are you put the basis elements of m here and then you put basis elements here, okay, and then you act A. So, since these are all basis vectors, C is non singular. Okay. And by this assumption that m and n are invariant under A, you can easily check that this C is just A1, A2. Okay. So, this submatrix, so this is corresponds to M and this corresponds to N. Because if I act A on these basis elements which are in M and the result is again they are back in M. So, each action is again a linear combination of vectors of these things, and that is expressed like that. So, in other words, so if you have two subspaces invariant under M and whose direct sum is R n, then the matrix with respect to that basis decompose into a block matrix. So, in other words, what we have is C inverse A C is A 1 0 0 A 2, and this is easily extendable to finitely many subspaces. So, let me just state that thing. So, let M 1 M k be subspaces of R n such that each M j is invariant under A. That is one condition, and then I have M j intersection M L is just 0, j different from L. So, they are mutually disjoint, and the third condition. So, R n is direct sum of M k. With these conditions, then there exists non-singular C such that C inverse A C is A 1 A k. So, in other words, in such a situation we can find a similar matrix which is a block diagonal matrix. Satisfying this condition. Okay. So, this is important. Okay. In this case, immediately we see that C inverse E A C is E A 1 etc. E A k. This we saw yesterday. Okay. Once the matrix is block diagonal, its exponential is very easily computed, and now we proceed to find some special subspaces of R n which are related to A and which satisfy this hypothesis of this thing, so that we have a similar block matrix which is similar to A. Okay. So, that is our next TM. Okay. Okay. That is so, yesterday I introduced the concept of spectrum of A. So, this is just spectrum of A. So, denoted by SP of A. So, this is set of all eigenvalues of A. Okay. Though A is a real matrix, an eigenvalue of A could be real complex. Okay. So, let us split this into two parts. So, let us lambda 1 lambda r. So, these are real eigenvalues counted with multiplicity. Okay. And then this we have mu 1 mu s. So, these are non-real, and since the characteristic polynomial has real coefficients, we also have this mu 1 bar mu s bar also eigenvalues of A. Okay. So, these are also non. So, they always occur in pair. Okay. So, the total number, because we are counting multiplicity. So, therefore, we have r plus 2s is equal to n. So, this is the order of the A. And this is also the degree of the characteristic polynomial. Characteristic polynomial, right. Okay. So, now just pick okay. So, let lambda belongs to spectrum of A, also real. Okay. So, complex case is similar. Okay. So, let K be the algebraic multiplicity of lambda. Okay. So, this is the multiplicity of lambda as a root of the characteristic polynomial. That is okay, right. So, there is another notion called geometric multiplicity. So, for that we have to introduce a subspace. So, let A n1 be kernel of A minus lambda I. Okay. So, this is the null space of or kernel of this A minus lambda I. Okay. So, this is referred as eigenspace of A corresponding to lambda. So, if lambda is an eigenvalue, we just form this, and this is a subspace of. So, n1 is a subspace of Rn. So, in case of complex eigenvalue, we take the real and imaginary parts of the eigenvector, and still we get a subspace of Rn. That is important, that you keep in mind. So, the dimension as a subspace, it has a dimension of n1 is called the geometric multiplicity of lambda. So, let me just state a fact that geometric multiplicity is always less than or equal to algebraic multiplicity, and the difference is referred to as deficiency of lambda for any lambda. Okay, so, that is always true, lambda in spectrum. Okay. So, the good case is when geometric multiplicity is algebraic equal to algebraic multiplicity, then we will have sufficient number of eigenvectors spanning this subspace n1, and a difficult part is when this is strict inequality. Okay. So, so in that case what we do is, so now define in general. So, define n j kernel of a minus lambda I to the power j. Okay, so you do it j equal to 1, 2, etc. Okay, so n1 is the eigenspace that we have defined, and we have this chain. Okay, it's very easily checked that this is ascending chain of subspaces, and since we are in a finite dimension, this chain cannot continue for long. So there exists smallest d bigger than or equal to 1 such that n1, n2, nd after which they are all equal. So there are no more additions of new non-zero vectors. Okay, so this is smallest. Okay, it has a name, and this is called index of lambda. So everything is, we have fixed an real eigenvalue lambda, and we are just discussing about that. So it again one more fact. So these are all subspaces. Okay, this n1, n2, nd are invariant under A. Okay, so let me not stress that again and again. So that's invariant subspaces of Rn, and more importantly, and dimension of Nd is equal to algebraic multiplicity. So when geometric multiplicity of an eigenvalue is strictly less than the algebraic multiplicity, we have to go for some more linearly independent vectors in order to get the full dimension, namely its algebraic multiplicity. We want to reach the algebraic multiplicity, and this is the way one reaches that thing. Okay. So you know you do this for every so if okay, so let mu be a non-real eigenvalue. Okay, and again you form the same thing. Okay, there is this one, there is no problem. Kernel of a minus mu I j equal to 1 to n, and it will have some index. Now you just consider the real and imaginary parts of vectors in these NJs. That is all you have to do, because remember we want to find only a basis for Rn. Okay, so we want only the real vectors, and when there are complex eigenvectors you take the real and imaginary part. They are not eigenvectors, but they are linearly independent as we saw yesterday, and that will do our job. Okay, so in this way, okay, so let me now just put this together. So for each lambda in the spectrum of A, real or non-real, it does not matter, we thus form invariant subspace. So, let me call it n lambda of R n, that is important. Okay. This subspace is in R n such that dimension of n lambda is algebraic multiplicity of lambda if lambda is real, otherwise it is 2 times algebraic multiplicity if lambda is non-real, because that count has to be proper. Okay. Because when lambda is non-real, lambda bar is also an eigenvalue. So, it has to be counted twice. So, that is why this twice and they are all invariant under A, and by very choice. So, we also have that n lambda intersection n mu is just 0 if lambda is, that is by very construction you see that. Okay. So, therefore, so R n is written as, so let me just write lambda 1 lambda r. So, this corresponds to real eigenvalues, and then I have n mu 1, this n mu s. Okay. So, I am not writing the mu 1 bar mu s bar because they are already included here. So, these corresponds to real eigenvalues and this corresponds to non-real eigenvalues. Okay. And these dimensions perfectly match, and that is why we have this inequality. And now you just use the fact we already stated, since all these are invariant. Okay. So, these subspaces are invariant. So, therefore, there exists a non-singular C such that C inverse A C is now A 1 A 2 A r, let me write lambda 1 lambda mu 1 mu s. Okay. And the next task is to find a suitable basis in each of these subspaces, so that this block matrices have a very simple structure. Okay. That is what we are going to do next time, next to it. So, instead of doing for a general thing, so let me just illustrate by a case. How to do that? Illustrate this by a case. So, how to choose a specific basis in NT. Okay. So, so suppose lambda is a real eigenvalue, of algebraic multiplicity 4 and geometric multiplicity 2. So, I have n 1, n 2, n 3 say, okay, and this dimension is 2, dimension is 3, and this dimension is 4. Okay. Suppose I have this situation. Okay. There are other possibilities. So, let us take one such possibility. And now, I would like to construct a basis where A is simplified to an upper triangular matrix. Okay. So, choose x in n 3 such that x is not in n 2. This is possible because this dimension is 3 and this is dimension 4. So, there is at least one non-zero vector which is in n 3 which is not in n 2. That is fine. Okay. Now, you form this x a minus lambda I x and a minus lambda I square x. Okay. So, this is in n 2 by very definition, and this vector is n 1. Okay. And these are all non-zero. In fact, these are linearly independent. Check that are linearly independent. Okay. And now, this is a non-zero vector in n 1, but dimension of n 1 is 2. So, choose. So, let me call it u 1 in n 1 which is linearly independent of. So, let me put some name. So, this let me call this as u 2 and this one u 3 and this one u 4. Okay. If you change the order, the matrix will change. Okay. So, that is what we will see now. Okay. And now, you add this u 1 on these vectors u 1, u 2, u 3, u 4. Okay. And u 1 is in n 1. So, this is just becomes lambda u 1 and u 2 is also in n 1. So, that becomes just lambda u 2, but this is not in this u 3 is in n 2. So, if you work it out, you would see that lambda u 3 plus u 2, and similarly you get lambda u 4 plus u 3. Okay. So, let me write this the same form u 1, u 2, u 3, u 4, and now I write this matrix lambda 0 0 0 0 lambda 0 0 0 1 lambda 0 0 0 1 lambda. So, it is very easy to check. Okay, that is what we get by just writing this thing. Okay, and we see significantly here there is one block here and another block here. Okay, see, these are referred to as Jordan blocks. Jordan blocks. Okay. So, in general, the number of Jordan blocks corresponding to an eigenvalue is equal to geometric multiplicity of that particular eigenvalue. So, in this case we have the geometric multiplicity 2. So, we get 2 blocks. Okay. And if if mu is non-real, so just A plus I B, B non-zero, the Jordan blocks are bit complicated because the eigenvectors are complex. So, we have to take only real part and imaginary part. The Jordan blocks corresponding to mu are of the form. So, remember they always appear in pairs. So, here also we get 2 by 2 blocks. Okay. So, let me write just B 2 I 0 B 2 I 2, let me write that, etc. So, just okay. So, diagonal blocks. So, B 2 is 2 by 2 matrix, this A B minus B A, and I 2 is just 1 0 0, the identity 2 by 2 matrix. So, here in case of real thing we have just scalars on the diagonal, but in the complex case we have this 2 by 2 blocks. Okay. So, this is the only difference. Okay. So, let me summarize in detail now. So, this summarize. So, given a matrix M n R, there exists a non-singular C such that C inverse A C. So, let me just write J 1 J 2 J k, where each J L is a Jordan block corresponding to an eigenvalue of A. Okay. And we have, so if if the eigenvalue is real, then J L will be very simple, lambda 1 1, and each J L might contain several blocks. Okay. So, one of the, I am just, this is not the only possibility, there will be several blocks, and if the eigenvalue is non-real, then this will be just B 2 I 2 I 2. That is the only difference. Okay. So, in particular so we have this C inverse AC, not C inverse AC, exponential e to the j1 etc. Okay. And in the next 10 minutes I will just show you how easy it is to compute the exponential of each of these blocks. Okay. So, let me just again concentrate on that. So, let lambda be real and j is equal to, so I take one of the blocks. So, this is a square matrix of some order. Okay. So, so what is Ej? Okay, so that is the question. So, again a fact. So, let me just, so if A and B commute, that is AB equal to BA, then exponential of A plus B is equal to exponential of A exponential of B. So, just like exponential of a real number. Okay. And in general, if we have non-commutativity, then we may not have equality in this. E to the A plus B may be different from E to the A and E to the B. So, since addition is commutative, we also have this. Okay. And this easily follows from this binomial theorem, just like again real numbers. So, if AB equal to BA, then A plus B to the K is summation Kj Aj Bk minus J equal to 0. So, this you can easily prove by induction, and which in turn give this. Okay. So, that is the only thing involved. So, now we apply this to J. Okay. So, rewrite J as lambda I plus B. So, B is this matrix 1 1 1 1. So, everywhere 0 except the super diagonal, which is just all ones. And since this is identity, so these two matrices commute. So, we have this e to the j is equal to e to the lambda I e to the b, and this you can easily check. E to the lambda I is nothing but e to the lambda into I into e to the b. So, this is identity. So, we have just e to the lambda e to the b. And now, let me just expand this. So, this is by definition I plus b plus h. Okay. The important thing about B is a nilpotent matrix. B is a nilpotent matrix. That is there exists some r integer r such that Br is 0. Okay. So, this is a finite sum. So, it only goes up to Br minus 1 by r minus 1 factorial, and it is very easy to compute even the powers. So, this the diagonal containing ones will be just shifted above and above. So, it is very easy to compute. So, and we have this thing. Okay. And in case lambda is non-real, so mu, suppose mu is non-real, then we have this j as block I2 etc. Still we can use, so this will write it as this B2 plus again same thing 0 I2 0 0 I2 etc. So, again this is nilpotent and these two commute. Okay. So, it is very easy to find, therefore, e to the j is again e to the B2 into I plus. So, let me call this matrix as some D. So, I have D plus D square etc. So, this is finite sum. So, there is no problem about that, finite sum. And leave as an exercise. So, remember B2 is A minus B, B A, okay, just 2 by 2 matrix. So, it is very easy to compute that. So, compute e to the B2 is equal to e to the A minus okay, let me just write that e to the A cos B minus sin B cos B. Okay. So, it is not difficult to compute that. Okay. So, finally, let me just take this theorem. So, we just combine all these things. So, suppose spectrum of A is a subset of lambda in C such that real lambda is strictly less than 0. Okay. So, then there exist constants k positive and sigma positive such that the matrix norm of e to the T A is less than or equal to k e to the minus sigma t for all t. So, this is important. This is not valid for all t, only for t negative, and just you have to use is you have this Jordan form J1 J2 Jk. So, therefore, you have e to the Ta is less than or equal to norm of C inverse, norm of C and then you have norm of this matrix e to the t j 1 e to the t j k, and this is just a constant, you leave it, and this we have already seen that this is less than or equal to maximum of e to the t j l, because this all block diagonal. And now if you use the previous representation, you see that sigma can be taken as minus half maximum of let me just minus real lambda in the spectrum. Okay. Okay. So, this is an exercise, you can just find that this is can be estimated less than or equal to e to the minus sigma t, some constant. Okay. I will put another constant here, constants will come. Okay. So, there will be some polynomials here, polynomials in t coming from this term, and that will be killed by half of this another half. So, that is how you get only half, any fraction will do. Okay. So, with that we conclude this preliminaries on linear algebra. You can work out several things in the some good text on linear algebra and fill the details that are left out in these 2 hours. Thank you.